All right, in this video, I just wanted to do a series of integrals that look really similar, but then you have to do in very different ways. And they get a little harder as we go down the list. Okay, so we're going to start out with our good friend, just the integral of 1 over x dx. And this one, if you remember that the derivative of the natural log of x is 1 over x, then this one's pretty straightforward. So you just get natural log of x plus c. If I change it very slightly, and I make it the integral of 1 over x minus 4, I can just do like a little u substitution, u equals x minus 4. And if u equals x minus 4, then du equals dx. And so it's really just a 1 over u. It's just natural log x minus 4 plus c. And you can check your answer by taking the derivative. Technically on those answers I should have the absolute value of x for natural log of absolute value of x. If I did, however, 1 over x squared, then I get a completely different situation. 1 over x squared is the same as x to the minus 2 power. And so I can actually just apply the power rule, add 1, and divide by my new power. So you can write it like that, or you can write it as negative 1 over x plus c. Those are both the same. So small change, totally different answer. Now, if I tried to do 1 over x squared minus 4 dx, you might try following the same sort of pattern as the natural log of x minus 4 one. But if you tried that, it won't work out. So I'm going to write down an answer that is not correct, and then I'll show you that it is not correct. Like, let's say that I just tried to do negative 1 over x minus 4 plus c. If I tried just by following the other example, if I tried doing that, and I did the derivative of that, remember that's the same as negative 1 x minus 4 to the negative 1. So then the derivative would be 1 x minus 4 to the negative 2 times 1. And that looks kind of promising. You can write that as 1 over x minus 4 squared. But you might notice the squared is on the outside of the parentheses instead of on the inside. And so then the x minus 4 squared becomes x squared minus 8x plus 16. So that's unfortunately not going to be the correct answer. So I'm going to clear the screen, and we'll actually do the 1 over x squared minus 4 correctly. What I notice, though, is that the bottom can be factored to be x plus 2 times x minus 2. And then that means that I can split it up into two separate fractions. One of the fractions over x plus 2, and one of the fractions over x minus 2. The only thing that remains to be seen is what are the numerators of those fractions. If I take this 1 over x plus 2 times x minus 2 and set it equal to this, I can multiply both sides by x plus 2 and by x minus 2, basically cross multiply, and I have 1 equals a times x minus 2 plus b times x plus 2. Plugging in x equals 2 tells me that 1 equals, if I plug in x equals 2, that tells me that 1 equals a times 0 plus b times 4. In other words, b is 1/4. And if I plug in x equals negative 2, I get 1 equals a times negative 4 plus b times 0, which tells me that a is negative 1/4. By the way, you could have plugged in any two x values and solved your system of equations. I just chose two x values that would make part of it eliminate, so it would be the easiest x values to use. All right, I'm going to come over here on the left side of the screen, Now I know that my original integral can be rewritten as negative 1/4 over x plus 2 and positive 1/4 over x minus 2 dx. And each of those are just those natural log situations that I was showing you earlier. Natural log x plus 2 and 1/4 natural log x minus 2 plus c. You can use your log properties if you want to pull the 1/4 in front. When there's subtraction, you can switch that into division, and you can write it like that. And then if I used my derivative just to check my answer, I would get 1/4 times natural log derivative, which is 1 over the inside function, times the derivative of the inside function, which is a quotient rule. So f prime g minus fg prime all divided by g squared. And this might look very different from the 1 over x squared minus 4. But please watch how things cancel out. It's kind of nice when you see it. This x plus 2 here cancels one of the x plus 2's there. This 1 times x plus 2 and this minus 1 times x minus 2 cancels the x's and leaves me with 2 minus negative 2. 2 minus negative 2 is 4, canceling the 1/4. What's left over? 1 on top, x minus 2 and x plus 2 on the bottom, which is exactly the original integral. So, tiny change, much different process. Let's make one more tiny change, and we'll see again a much different process. The last one was 1 over x squared minus 4. What if I change it to 1 over x squared plus 4? Well, now I can't factor the bottom. So I can't do that partial fractions decomposition. I can't do the natural log problems. So instead, I recognize that this looks kind of like a squared plus b squared. Then I draw a triangle. A squared plus b squared equals c squared. So I know that the hypotenuse is x squared plus 4. I'm going to call this angle theta. And I'm actually going to switch the x and the 2 just because I like it more when x is the opposite side. And you'll see why in just a second. If I look at my triangle here, I can write that tangent of theta is x over 2. I just want to be clear, I could have used x on the adjacent side, I just would have had a cotangent of theta, and that's just slightly more annoying because cotangent has negatives in its derivative. I'm going to take the derivative of tangent, which is secant squared theta, d theta. I'm going to take the derivative of x over 2, which is 1/2 dx. The other thing I'm going to do is I'm going to try to match my integrand. So if I look at cosine of theta, that's adjacent over hypotenuse. And that tells me that if I did cosine squared of theta, that would be almost exactly the integral that I was looking for. Because if I square it, it gets rid of the square root. So now I know that 1/4 cosine squared theta is the integrand. And I also know that 2 secant squared theta d theta is equal to dx. So my original integral can be replaced with 1/4 cosine squared theta, and then my substitution for dx is 2 secant squared theta d theta. 2 and 1/4 are constants, so it's just 1/2. Cosine and secant are reciprocals. Secant's just 1 over cosine. So cosine times secant is 1. Well, the integral of 1 is just theta. So I have 1/2 theta plus c. That's an unsatisfying answer because what the heck is theta? I asked a question that had to do with x, and then I give an answer that has to do with theta. If you go back and look at your original trig function, tan of theta is x over 2. That means we can write this as 1/2 arctan of x over 2. Arctan is the inverse of tangent, so if you have tan of theta and you want to solve for theta, then theta equals arctan of the other side of the equation. So look how different that answer is compared to when I had x squared minus 4. Very minor changes to the original problem can lead to completely different integration strategies. I'll show you one more. I'm not going to go all the way through it, but I'll talk about how we could go through it. Let's say I had integral of 1 over x to the 4th minus 16. Well, we could start by factoring the bottom, 1 over x squared plus 4 and x squared minus 4. Then we could split up our partial fractions. But you got to be careful. I like this one. You got to be careful there with the partial fractions decomposition, because those are quadratic pieces. So you really have a linear term over a quadratic plus a constant over one linear factor and another constant over another linear factor. From there on out, it's pretty much a repeat of what I've already showed you. So there you go. Please let me know if you have any questions. Happy to help out.